The discovery of the source of a ghost particle from beyond our solar system created a huge stir in the scientific community when it was announced in mid-2018. But what exactly is a ghost particle, and what does this discovery mean?
Hey everybody, welcome to Studio 64. My name's David. I've been searching the interzones for some more science, space and tech news to share with you, and I came across this at Science Alert. Yes, ghost particles could be the secret behind the heaviest elements. This should be interesting. Yes, big atoms demand big energy to construct. A new model of quantum interactions now suggests some of the lightest particles in the universe might play a critical role in how at least some heavy elements form. Yes, physicists in the US have shown how subatomic ghost particles known as neutrinos could force atomic nuclei into becoming new elements. Interesting. Not a physicist myself, but if there are any physicists out there watching this video, please feel free to comment on it because we'd love to hear from it. I just love sharing all this news and science stuff. I think it's fantastic. And as usual, I'll leave a link to the main article below the video. So pop in, check out the embedded links, go for a bit of a deeper dive beyond the main article. Makes for an interesting read, believe me. Now, not only would this be an entirely different method for building elements heavier than iron, it could also describe a long synthesized in-between path that sits on the border between two known processes, nuclear fusion and nucleosynthesis. Now, for most elements larger than hydrogen, the warm hug of a big bright star is enough for protons and neutrons to overcome their strong need to push apart, long enough for other short-range interactions to take over. This fusion embrace frees additional energy, helping the cores of stars remain toasty warm. Now, once atoms grow to around 55 nucleons in size, the mass of an iron nucleus, the addition of extra protons requires more energy than the process of fusion can possibly repay. Now, this shift in thermonuclear economics means that the periodic table's heavyweights can only form when additional neutrons stick to the congealing mass of nuclear particles long enough for one to decay and vomit out an electron and a neutrino, transforming it into the extra proton required to qualify as a new element. Interesting choice of words there. Yes, here we go. Neutrons transform into protons when they decay, emitting an electron and a neutrino. There's your electron. That's really interesting, isn't it? So you've got your electron and a neutrino being ejected. Again, I'm not a scientist. I'm just trying to understand this and, love sharing it with everybody. Science, space, and tech news gets me all excited down in my nerdy nether regions. But then again, my personal life is no concern of yours. Yes. Now, ordinarily, this process is painfully slow, trickling away over the scale of decades or even centuries as nuclei within large stars jostle, gaining and losing neutrons frequently, with few ever making the switch into protonhood at the critical moment. Now, given enough of a punch, this growth can also be surprisingly quick, in a matter of minutes in the hot mess of collapsing and colliding stars. Now, we've got a little video here, not this particular one, but we have a little video on ghost particles and what they are. This should be very interesting. Let's check it out, then we'll carry on the conversation when we come out the other side.
The ghost particle. What does it mean? The discovery of the source of a ghost particle from beyond our solar system created a huge stir in the scientific community when it was announced in mid-2018. But what exactly is a ghost particle, and what does this discovery mean? Otherwise known as neutrinos, ghost particles are elementary particles with no electric charge and almost no mass. This neutral electric charge is where it gets the name neutrino from. Due to their lack of charge and mass, they don't interact much with their surroundings, making them extremely difficult to study, like trying to find a black object in a dark room with your eyes closed while wearing a blindfold. Even after the existence of ghost particles was first postulated back in the 1930s, it took 2 decades for scientists to successfully detect them. The ironic thing is that these particles are all around us. In fact, our bodies are exposed to trillions every second. So where do these mysterious, non-interactive particles come from? Most come from our very own sun, but the origin of other high-energy neutrinos is more mysterious and seems to be somewhere out in deep space. Neutrinos are closely connected to cosmic rays, high-energy particles whose source has also remained elusive and whose interactions with other atoms can produce neutrinos. Unlike neutrinos, however, whose path across the universe follows a direct line, cosmic rays interact with magnetic fields and their path can be erratic. The first signs of cosmic rays were encountered in 1909 by German physicist Theodor Wolff, who developed a device to detect energetic charged particles and found that there were higher levels of radiation at the top of the Eiffel Tower than at the bottom. 3 years later, in 1912, Austrian-American physicist Victor Hess ascended into the atmosphere in a hot air balloon with modified Wolf electrometers and confirmed that there's more radiation higher up than near the ground. By conducting his experiment during a near-total eclipse, he concluded that there must be another source beside the sun. While scientists have had theories as to the origins of these non-solar neutrinos and cosmic rays, none could be proven until specialized equipment was made to study them, such as the detector at the IceCube Neutrino Observatory. Completed in 2010 at the Amundsen Scott South Pole Station in the Antarctic, this highly specialized installation is designed to detect and study ghost particles. The IceCube sensors consist of optical spheres called digital optical modules, which are connected via strings and placed up to 2,450 meters into the ground. Once deployed, 2 staff members monitor the equipment for any signs of the elusive particle. One of the few ways that a neutrino interacts with anything is by creating a secondary charged particle after colliding with an atom, and in 2017, one such interaction was detected and dubbed IceCube 170922A. Once detected, an alert was sent out to several other observatories to help trace the place of origin of this particle. A total of 18 observatories, including the Major Atmospheric Gamma Imaging Cherenkov Telescope and NASA's Fermi Gamma Ray Space Telescope, collected data on the source of the neutrino and measured the whole electromagnetic spectrum from radio waves to gamma rays. After some number crunching, it was determined that the source of the ghost particle was a blazar known as TXS 0506 plus 056, one of the brightest objects in the universe. Blazars were first thought to be irregular stars from our galaxy, but are instead large galactic nuclei which emit powerful beams of gamma rays and irregular beams of electromagnetic radiation from outside our galaxy. It's believed that blazars are powered by black holes in their center. Black holes are born when massive stars come to the end of their life cycle and collapse. As such, they have a strong gravitational pull, and the accretion disk around them generates a huge amount of energy. Thanks to this process, they act like giant particle accelerators, beaming particles across the universe. These pass through us daily, bathing the Earth in a constant stream of energy from distant galaxies. In tracking the neutrino IceCube 170922A back to its origin, scientists killed 2 birds with 1 stone, discovering something about cosmic rays as well as neutrinos. We now know that neutrinos and cosmic rays can come from blazars, a huge step in understanding how the universe works. By understanding neutrinos, we have another piece in the puzzle for multi-messenger astronomy, a type of astronomy that interprets 4 main types of extrasolar energies: neutrinos, electromagnetic radiation, cosmic rays, and gravitational waves. Gravitational waves are generated from the curving of space-time by massive objects. Electromagnetic radiation is generated by accelerating electrically charged particles. Combined, these sources can tell us a lot about our universe. Our cosmic equation is far from complete, but now it makes a little more sense. With this new information about ghost particles and cosmic rays, we can put to rest old questions and begin formulating new ones. It's an exciting time for astrophysics. What will these lessons lead us to in the future? And what new discoveries are waiting just around the corner?
Well, that was intensely interesting. I love that sort of stuff. As I said, I was unaware of what ghost particles were. So that's given us a little bit of extra background. It's absolutely fascinating, isn't it? But some theoretical physicists have wondered if there are other pathways, intermediate ones, between the slow, or S process, and the rapid, or R process. Now, where the chemical elements are made is not clear, and we do not know all the possible ways they can be made, says the study's lead author, University of Wisconsin-Madison physicist Baha Balantikin. Yes, we believe that some are made in supernovae explosions or neutron star mergers, and many of these objects are governed by the laws of quantum mechanics. So then you can use the stars to explore aspects of quantum mechanics. Now, a solution might just be found in the quantum nature of the floods of neutrinos, the most abundant particles with mass in the universe that spill out into cosmic environments. Now, though virtually massless, with barely any means of making their presence known, their sheer numbers mean the emission and occasional absorption of these ephemeral ghost particles still exert an influence over the budgets of protons and neutrons buzzing about deep inside massive stars and cataclysmic cosmic events. Certainly makes you think, doesn't it? You know, we've got all these petty arguments we have down here on planet Earth, and you've got stuff like this which is even smaller than us, and it's doing things that actually help shape the universe. Meanwhile, we're behaving like childish, mindless, squabbling primitives. Fascinating, isn't it? Like little kids in a sandbox arguing over a toy. That's human beings. Fascinating. One bizarre quirk of the neutrino is its habit of oscillating within a quantum fuzziness, switching through several flavors of identity as it flies through empty space. I wonder what it identifies as. You know, neutrino might identify as a blue-haired non-binary wombat on Thursdays or something. Oh boy, David, you bigoted fat son of a bitch. Fascinating. No, I just find it amusing, that's all. Modelling vast numbers of neutrinos flipping and flopping flavors within a chaotic nucleon soup is easier said than done, so physicists will often treat them as a single system, where the properties of individual particles are considered as one big entangled superparticle. Now, Balantikin and his colleagues from George Washington University, the University of California, Berkeley, used this same approach to better understand how winds of neutrinos emitted by a newborn neutron star slamming into the surrounding environment could serve as an intermediate process of nucleosynthesis. Yes, by determining the extent to which the quantum identity of individual neutrinos depends on the extent of this entangled state, the team found a significant quantity of new elements could be generated by this ghostly storm. Very interesting. This paper shows that if the neutrinos are entangled, then there is an enhanced new process of element production, the I process, says Balantikin. Now, while the numbers add up in theory, testing the idea is a whole other matter. Now, studying the interactions of ghostly neutrinos on Earth is still in its infancy, leaving researchers to stare into the distance of space in search of evidence of new ways the biggest elements come together. Yes, and this research was published in the Astrophysical Journal. So as usual, with that link to the main article below the video, pop in and check these out, these links. It's absolutely amazing. Absolutely incredible. Yes, ghost particles will be the secret behind the heaviest elements. This, as I said, I don't understand enough about theoretical physics, and this is why I love, searching these articles and sharing them with everybody. Because the more knowledge we gain, the more interesting it's going to become. As I say, I'm not a scientist myself, but I love all science and technology. So whether it's, aerospace engineering, whether it's, geology or exoplanet geography, you know what I mean? All this sort of stuff, biology, exobiology, you get the chemistry, you get the idea. I just love all science, and as I said, just love sharing it with everybody, and love to hear your thoughts too on this. It's absolutely incredible. All right, well, my name is David. Thanks for joining me for another Studio 64 Science, Space and Tech News update. I shall see you in the next one. If you enjoyed this video, please like, share, subscribe. I greatly appreciate it. If you're up for it, drop a comment down below the video, because I'd love to hear what you think. All right, take care, and as I always say, if you can't be good at it. And as I also always say,
please, Spock, do me a favor, and don't say it's fascinating. No. But it is interesting.